Bismillah ar-Rahman ar-Rahim. Welcome to another session on EE206, Introduction to Electrical Systems and Computations. And we devote this session for the subject of electromagnetics and fiber optics. We start with the subject of electromagnetics. And let's start by electromagnetic waves. These are waves that travel in space with the speed of light. Now they travel in space. In fact, they travel in vacuum also. They are not like sine waves, which are mechanical waves, which need some particles. They use the particles of the media to travel. No, electromagnetic waves travel in space with the speed of light. Now there are many ways of generating those electromagnetic waves, two of which are the atomic emission. When the electron leaves an orbit to a lower energy orbit, it radiates this energy in the form of electromagnetic waves. But the more important way of generating EM for us in electrical engineering is that through a changing current, or what we call it an AC alternating current. When we let a current flow through a wire, an alternating current through a wire, then this wire generates or radiates the electromagnetic waves, and this is what we use actually for wireless communication. Okay, now let's examine this spectrum. We've come across the term spectrum before, if you recall, in one of the sessions. We talked about the frequency spectrum of the signal. Now this is the full spectrum, or a big portion of the spectrum of electromagnetic waves. Let me explain a few things on this chart first. Okay, on the lower axis, this is the frequency axis. Okay, so these are the frequencies from a few hundred hertz to giga and tera and higher frequencies. That's the lower axis there. The upper axis is the wavelength in meters. These are the two main properties of waves, the wavelength and the frequency. And in fact, they are related, as you recall from your physics. If you multiply the frequency of the wave with its wavelength, you get the speed of light, which is a constant 3 times 10 to the 8 meters per second. So actually, each value in the lower axis has a corresponding value on the upper axis. We have the frequency in the lower axis and the wavelength on the upper axis. So these are, this is the EM spectrum. You can notice that parts of the spectrum are given certain labels. This is some in the communities of electromagnetics and communications. They agreed on certain terminologies. For example, frequencies between 3 kilohertz to few gigahertz are called radio waves. Frequencies above 1 gigahertz are called microwave range, and so on. So you have the radio wave range, the microwave range, and so on. Part of the spectrum, as you see, is the visible light spectrum. This is the range of spectrum of the light. So the frequencies, these frequencies are visible to us in the form of the known colors. Now the band just below that band is called the infrared. The one just above this is called the ultraviolet. And you have some other labels there. So that's the full EM spectrum. What we notice on this chart as well is we have shown the frequencies allocated to some of the communication systems, the main communication systems, for example, AM, FM, satellite communication, TV, and so on, the mobile, the GSM, and so on. Each of those applications, or each of those communication systems, are agreed upon internationally through the International Telecommunication Union that they should be allocated certain frequencies. So AM worldwide is allocated a certain frequency for broadcasting. FM worldwide is agreed to broadcast in a certain band. Satellite communication is given a certain band. GSM is given a band. In fact, it's given 2 bands. And these are shown here. So you can see on this spectrum what part of the spectrum is allocated or assigned to what communication application. Now, of interest, probably you've noticed that the communication applications are sort of congested in a certain band. You can see that if you go to the lower side of the spectrum, there are no communication applications, no broadcast, nothing, no broadcasting applications, as well as if you go to the higher frequency or the higher part of the spectrum, okay? And that's worth explaining why we don't have, assigned communication systems or broadcasting in the low side of the spectrum. We've answered, in fact, this question in one of the sessions before. If you recall that, we said that the size of the antenna you need for broadcasting is related to the frequency of the signal or to the wavelength of the signal. And if the signal has a low frequency or a large wavelength, then the antenna size would be huge. This is why it's not feasible to design antennas for broadcasting at very low frequencies. So we don't see any broadcasting in the low part of the spectrum. Now, the reason that we also don't have applications in the high part of the spectrum is that these frequencies are too high for us to really generate and process, and the technology we have in hand today does not allow us to go that high. I'll give the example of building sky towers or sky buildings. What stops you from going higher and higher in building your tower? In fact, there is no limit. The sky is, as they say, that the limit is the sky. You can go up and up. But what limits us in going to only 100, for example, a few hundred meters or so, is the technology we have to penetrate those high altitudes. So the same analogy is here. The high frequencies are too high for us, for the technology of today, that we really don't have many applications in this range. But once we learn more, we can generate higher frequencies, process higher frequencies, probably will invade more into that part. So that's a very interesting or very important piece of chart that a communication and electromagnetic engineer should know and understand. Okay, now, how do you broadcast? How do you use those frequencies? How you use the EM spectrum? We mentioned this before. We use the antennas. Antennas are the transducers that allow me to convert current into waves if it's a transmitting antenna. So if you see on the upper plot here, you have a source, that's your signal, your alternating current, going through a wire, and the wire then radiates the waves. Now, if it's a receiving antenna, again, the falling electromagnetic waves would hit the antenna, and then that will generate current in that wire or in that antenna in general, that we take to the load, which could be our speaker or monitor or whatever. Okay, so the antenna is again the device that we use for generating EM waves and receiving EM waves. Antennas come in different shapes. The one I'm showing here is the monopole antenna. That's the simplest one that you can see around in cars, in Wi-Fi access points, and so on. These are the monopole antennas. But we have other shapes. The parabolic antenna is very common and famous also. We use for satellite TV reception. We have the horn antennas used for microwave link, to connect different areas with microwave. We have the cylindrical antennas, typical for GSM communication, towers, and so on. We can have, in fact, an array of antennas stacked together, as in the Yagi antenna, an array of wires or pieces of wires that's used to, or is usually used for the old TV systems, And you also can, for example, as we've seen in the last chart here, have an array of parabolic antennas, and this generates a very focused beam that is usually needed for space or communication or astronomy. So as you see, antennas come in different shapes, different sizes, because they have different applications. Now, one of the characteristics of the antennas is the radiation pattern. Now, I want you to think of the antenna, as it generates waves. So just think of those waves as smoke. It generates or produces smoke. Now, this smoke takes a certain shape. That's what we call the radiation pattern of the antenna. The radiation pattern of the antenna. We can either show it in a two-dimensional plot, as you see on the one on the left, or at the three-dimensional plot, the one on the right. Now, what are those, lobes and so on? Actually, you can think of the antenna as being in the center of the circle, and this shows the radiation pattern. Basically, it shows the strength of radiation at different angles. The strength of radiation at different angles. So this shows that for that antenna, you have, the highest or the strongest radiation is in this direction. There is also a good amount and energy of radiation in that direction and slightly at the back. And there are points where almost there is zero radiation. If you come to the antenna from that angle, that specific angle, which we call it a null, you don't in fact get anything. That's if it is a transmitting antenna. If it's a receiving antenna, it means that it will receive signals coming in this direction very well, but signals or waves coming from the null points would not be received or received with a very, very low amount. So the radiation pattern is important in the design of antennas, so to know how it radiates and how it would be efficient for reception if it's a receiving antenna. Talking about radiation patterns, we have broadly speaking, two different types. We have what we call the omnidirectional antenna. This is an antenna that radiates the waves in all directions with almost the same power. So we call it omnidirectional. Okay, as you see here is that sphere representation. So it radiates in all directions if it's a transmitting antenna. If it's a receiving antenna, it means it receives from any direction. That's the omnidirectional antenna. But in some applications, we're looking for, directing the beam in a certain direction. We call them directed antennas. And usually directions are made through arrays. So we generate a pattern that is focused, that is along or across a certain zone of angles. So the transmission is, concentrated into that direction. The reception is best when the wave is received from that direction and so on. Now, why do we have different patterns of antennas? In fact, you could have a directed antenna with, for example, 2 branches or 3 branches, okay? So you can design the pattern you need depending on your application. Can you think of applications that would require omnidirectional antennas and other applications that would require some sort of directed antennas? Okay, that concludes the briefing on electromagnetics. Let's shift to the subject of fiber optics. What is an optical fiber? Optical fiber is a very thin glass. Basically, it's a pipe or a waveguide that guides light through. So it's a pipe or a waveguide that guides light through it from point A to point B. I'm carrying here a piece of an optical fiber, and let's just closely examine, the different parts here. We have a piece here, the last piece here, which probably you cannot see, but you can see that my finger is tipping on something. That's the core. That's the core. That's the thin glass in the middle of it. So this is the core. Okay. Now, on the top of the core, there is another layer of glass, or sometimes plastic, that's called the cladding. And basically, it's the core and the cladding are the main thing of the fiber. So it's the core and the cladding. The rest are just, covering for protection. So you have a coat, we have some, Kevlar fiber, we have some jacket. These are just for protection and just to protect it from being broken or so. But basically the main function is in the core and the cladding. So the core and cladding are both glass, but the cladding has a refraction index that is lower than the one of the core. And from your physics 102, you know that when the light, which is traveling in the core, try to escape the core, it hits the boundary between the core and the cladding, and because of the difference of the reflection index, there will be a total internal reflection of the light inside the core. So this way, we keep the light confined to the core and it travels for long distances. So that's more or less the internal structure or the cross-sectional structure of the fiber. Okay, now one of the main applications of the optical fiber is in communications. Now, if we want to use it as a channel, in this case, the signal will flow in the form of light. The signal has to flow in the form of light. So the fiber carries light, which means now we need some type of device or transducer that converts the signal into light format for transmission and then back from light format to the original format. Okay, so what are those devices? What are devices that will convert to light and back from light? So basically, unfortunately, we don't have a device that directly takes the message from its original format, speech or video or so, directly into light. We go through electricity also. So we convert the signal from original format into current, and then from current into light. We let the light travel through the fiber. On the other side, we take it back from fiber, or from light, sorry, into current, and then from current into original type of the message. And this is what you see in this block diagram of a communication system using optical fiber as its communication link. Now, what are those devices? What are those devices that will allow me to convert to light and back from light to current? The answer is diodes. You probably heard of light emitting diodes, the LEDs, or laser diodes, the LEDs. These are devices, when you let current go through them, they release photons, which are the main constituents of light rays or light beam. Okay, so on that side, we have the laser diode or the light emitting diode, which generates the light that goes through the fiber. On the other side, we have diodes made from other material that's called a photodiode. The photodiode is made of a material which is, when hit by light, basically photons, when hit by photons, it releases electrons from this material. So the light hit on the photodiode would release electrons, that is current. So on one side, then we're going to have a laser diode or LEDs. On the other side, we have a photodiode, and this way we have the full conversion to light and back from light. Now, what is special about transmission over optical fibers? What is special compared to the other, two channels, the wire and the wireless? The first thing is, a signal in any format, whether it is current or waves or light, will lose energy as it travels. So you always would lose energy as you travel through the channel. There is nothing perfect, nothing ideal. But light is the least among the three that loses energy as it travels, which means that you can really let your light signal go through the fiber into much longer distances compared to current and waves without the need of interfering and trying to amplify the signal. And that's one of the main advantages. So fiber can run for long, tens of kilometers without the need of interfering and trying to boost or amplify the signal, So that's one main advantage. The other advantage, talking about light, as you've seen in our EM spectrum, light is a high frequency waves, and because they are high frequencies, they allow us to transmit at very high transmission rate. Transmission at the rate of 10 to the 13 bits per second is not unusual over fiber, which means really you can have a huge amount of data rates for many applications. Just having here a numerical example, a rough one, with one fiber you can probably feed 10,000 houses with a 10 gig of internet connection. One last advantage of optical communications is security. It is secure. In what sense? When you transmit waves is, there in space, everybody can capture the wave, and unless your waves are somehow encrypted or ciphered, then people can listen to what you're transmitting. Also, if you transmit current through wire, current through wire would leak some radiations, and then you also can tap in and, get something of what's going on. Light is different. Light does not emit any radiation. So when you let light go through fiber, it's very secure, and no matter how close you get to the fiber, you cannot get anything. It does not radiate anything unless you really go and break the fiber. But if you break the fiber, you break the whole communication. So it's very secured in that sense. And because of the those nice properties, fiber has been used. Fiber networks are very common nowadays, and they uh, work as the backbone of the internet. The main connections on the internet are mainly fiber, and there are huge, thousands or tens of thousands of kilometers of network all over the earth that connects different countries and continents with fiber networks. This is the only one example, the FLAG network, the fiber link around the globe. It has been in operation since 1997 roughly. It's around 27,000 kilometers. It connects Europe, through the Middle East, through Japan, Far East, and so on. A huge network, and there are several other networks that connects also other parts. These, as I said, are used as the backbone, for the main highway of data. And then once you reach to one node, then you can take it from there through either another branch of fiber network or microwave or whatever. Thank you.